Welcome back. This is video 4.23 and the last of the videos for chapter 4. In this one we'll talk about data reliability and factor analysis and how having low item reliabilities in the data set can result in pretty poor factor analysis results. Now the text talks about creating simulated data at each of 6 levels of reliability by adding a random error component of various sizes. So they created data with a reliability of 0.90, which is 1 part error variance, and this is using a random number generator, and how they did this, to adding that to 9 parts of structural variance. So that's 1 part plus 9 parts. So we have 1 plus 9 equals 10. And then since 9 of the 10 was structural variance, we call this, this equals 0.90, excuse me, so we're calling this R90. They also did 1 part error to 4 part structural, so 1 plus 4 equals 5. Excuse me, that's 4 out of 5, giving us 0.8. So calling this R80. Okay. Next, 1 part to 2 parts. 1 plus 2 equals 3. 2 over 3 is 0.67, calling this R67. And then did the same thing, continuing 1 part error variance, 1 part structural. That will lead us to R50, so 0.5. And then we have 2 parts error to 1 part structural, and that's going to get, this one is 0.50, that's going to give us 0.33, so we're calling that R33. And lastly, say we have 3 parts error, 1 part structure, that's going to give us 0.25, so we're calling this R25. Notice on these last two, we have more error variance than structure variance. So as we see in the text, table 4.12 is a factor analysis summary table using maximum likelihood analysis. We have item reliability set at R equals 0.90. Now, although these results are for a maximum likelihood factor analysis, they would be almost identically the same for any of the other 4 analyses for which the simulation was done. So that is principal components, principal factor, iterated principal factor, or alpha. And that's because the results of the common factors methods differ little from principal components when the data matrices have a large number of variables, which we have a good amount here, and strong psychrometric properties. For example, a strong reliability, as we have here, 0.90. Now remember, we had 0.90, 0.80, and a reliability of 0.67. Even with the reliability of 0.67 simulation, there's no loading for a common factor method that deviated more than 0.03 from the principal component loadings. However, for all 3 of the lower reliabilities, 0.50, 0.33, and 0.25, the pattern of loadings does differ markedly among the different methods. Now moving on to figure 4.14, this displays the vector plots for the factor patterns at each of the 6 levels of simulated reliability. As you can see, for the first 3, R90, R80, and R67, they look pretty close, and it looks like the variables load pretty well in those factors. However, as we look at R50, R33, R25, we note a huge difference. So the line between an acceptable level of structural integrity and the factor loadings, or the reliability, seems visually to be somewhere between 0.67 and 0.50. That's where the structure begins to deteriorate for factor analysis. Now, figure 4.15 looks at the percentage of variance accounted for at each of the 6 reliability levels, and for errorless data shown for principal component analysis and for principal factor analysis. So here on the left we have the percent of variance accounted for, and notice we have the reliabilities here. So notice that the two methods are very similar in their values at the highest levels of reliability, R100, R90, R80, even R67, but they begin to diverge at the lower levels, 0.50, 33, 25. Now, if we were to add other methods of factor analysis, like the maximum likelihood, alpha, iterated principal factors, those would fall somewhere in between these two lines here, probably closer to the principal factor. Now, what we're learning about in this section is really important. Reliability concerns are obviously central to the question of when to stop factoring. That is, how many factors should be extracted. So from these simulations in the textbook, it becomes apparent that when the reliability of individual variables drops below 0.67, the question of how many factors are present usually can't be answered correctly. Once we get below 0.67, for example in 0.50, 33, and 25, we may be extracting more factors than is actually necessary. So once again, to drive home the main point of this section, from both the factor plots and also the factor scores of simulations, it's clear that to obtain factor loadings and factor scores that accurately reflect the true state of affairs, you should strive to have individual item reliabilities of 0.67 or higher in preparation for factor analysis.